Now this simulation is looking quite cool as it is right now, but we can also fine tune this a bit further by using some microsolvers that give us control beyond what's immediately available in the PyroSolver's top level controls. So if we dive inside our PyroSolver here, this takes you to an editable subnet inside this PyroSolver's DOPNet. So you can see when we double click the PyroSolver, it doesn't just go one level down into the PyroSolver. If you look at our path here, we've gone inside the DOPNet of the PyroSolver and then inside this editable subnet inside there. And you can click one level up to go to the DOPNet directly. And this shows you how the entire DOPNet is all wired together here. And if we scroll to the right a bit and zoom in, you can see this enabled forces one here, and that's not grayed out because this is editable. Everything else is kind of locked as it is. And this is quite nice because this gives us an easy way to add extra microsolvers to really customize how our sim is working. So if you hit tab and type in gas, you can see lots of volumetric related microsolvers that we can drop in to customize this behavior. And of course, we're not going to go through all of these microsolvers here. And most of these I've never had to use. They're really just a few key ones that I find myself using fairly often. So one of the useful ones is this gas damp here. So if you drop that in, this is sort of like a drag on the volume. It damps down the velocities in our simulation. So to add that to the sim, after dropping it in here, we can wire this into the force output tab. And this gas damp is very useful when you have a sim that's a bit too energetic and active, and our current simulation is fairly energetic and could look a bit better if it was calmed down and if those velocities were damped down a bit. So let's do a new flipbook after adding this gas damp. I'm not going to change any of these parameters just yet. Let's just do another flipbook now and see what it looks like. Now this updated version with the gas damp microsolver is looking quite cool. It's a bit too heavy-handed because it's really forcing all of the dust to just hang in the air, which is not a terrible effect. This does look kind of nice, but I do want the dust to be a bit heavier, and the gas damp is really preventing this from settling as much as I want it to, and the sim was a bit too active before. For comparison, let's bring up that previous version. And you can see how this version is extremely active and very energetic, and this one does have a nicer quality to it after adding that gas damp behavior. But yeah, it's too extreme, so we're going to back off on the strength of this effect and rerun our sim. So let's go back into our PyroSolver here. And then on this gas damp, I'm going to reduce it to about 10% of its current scale. We do have additional controls like this correction radius to prevent overly abrupt changes in the velocity. It kind of blurs out the effect a bit. We have a target speed. We have controls for remapping that drag based on the velocity. But I'm not going to worry about all of those controls. I'll just take our current scale on this value and try reducing that to 0.01, just so we get a bit of damping on our sim. And after reducing that gas damp scale, let's jump out of our PyroSolver here, and then do a new flipbook. Now things are looking much better with that gas damp toned down a bit. We're getting some nice calming down of the velocities in our sim. It's not quite as energetic and active. Things are looking a bit smoother, and it is lending a nicer quality to our dust sim. So I'm happy with how this is looking so far, and there's one more missing element that I'd like to add via these microsolver controls, and that is some wind force. So if you dive back inside the PyroSolver, we can add additional microsolvers by dropping in a merge just before the force output, and then we can merge together as many different microsolvers as we want to. So I'll drop in a gas wind, and we can connect this to our merge here, and we do have this unified wind direction on a control null at the object level here so that all of our various simulations and this entire scene can have a matching wind direction. So we can copy this parameter, go back into our Pyro solver, and paste a relative reference into this gas wind direction. And this relative reference is pretty annoying with the unnecessary ... So I'm just going to change this to object/control. It's totally fine the way it is here with all those dots. I just find it a little bit annoying. So now this gas wind is referencing that direction from the control null, and this is a totally fine way to add some wind force to your dust sim. However, I often like to add a more customized wind to my sim. So I like to have more wind force in the higher portion of the simulation that's further away from the ground. And for the ground areas, I like to use a bit less wind force. And we don't really have any way of controlling that with this standard gas wind here. So this is one case where I like to set up my own customized forces with a gas field VOP. So let's disconnect that gas wind and then drop in this gas field VOP and connect that instead. And I'll rename this to custom wind. And if you dive inside here, then this allows us to create some very customized behavior with some VOP networks here. And before we dig into setting up this custom wind and this VOP net here, I should also add that for the purposes of this class, if you just want to use the standard gas wind microsolver here, that's totally fine. I've given you a lot of stuff to try out with this week 6 content. The shockwave and dust setups should keep you pretty busy, so it's totally fine if you don't have time to do all of this custom VOPnet stuff, but it is valuable to start learning how to set up these really customized behaviors in VOPnets, and this is what I used for my version. So, in our VOPnet, we have all of these various inputs, which can be very helpful information. We have our density, we have the position of the current voxel that's being processed, we have some information about the bounding box and the current time and frame and etc. And all of this is potentially valuable info when setting up customized behaviors. And our default VOP output here is just writing to density. So right now we're connecting density to density, so you can do whatever processing you want. Like if we wanted to reduce our density in half, we could drop in a multiply constant, drop that on this line connecting our density input to output, and set our multiplier to 0.5, and this will reduce our density by half on every time step of our DOP simulation. However, for this custom wind setup, I don't want to change the density at all, so let's just disconnect that, and we're going to work on the velocity instead. So to work on other fields in the simulation, we can drop in a bind to read that field in. I'll call this vel and set the type to vector. So then this reads in that velocity and we can do some stuff to it and then write that back out. So to write that out, I'll drop in a bind export. I'll also call this vel. I'll set this to vector, even though that's probably optional because it should just use a vector output anyway once we connect our vector input to this. So now we're reading in velocity and writing that back out, and then we can modify this in between. So in this case, I want to read in the desired wind velocity, and then we're going to push our current simulation velocity toward the wind velocity. So let's drop in a parameter. I'll call this wind and set the label to wind as well. The type is going to be a vector. And when you create this parameter like this, this also creates a parameter available on this gas field VOP as well. So if you exit that VOPnet and look at our interface here, you can see that this has added that wind parameter here. So we've already copied a relative reference into this gas wind microsolver. So I'll just right click that wind direction, copy that parameter, and then on our gas field VOP, I'm not going to paste in a relative reference. I'm going to paste expressions or channels. So after pasting that in, you can see this is just putting in the same relative reference to the control null that this has here. It's just copying that same expression into this parameter, just because I would rather have this linked directly to the control null than have it linked to this gas wind microsolver that we might just delete. And now to push this velocity in the direction of the wind, we can find the difference between these two vectors. So I'll drop in a subtract, connect this wind parameter to that, and then connect the velocity to the subtract as well to get the difference between them. And now that we have this difference, we can add the difference to the current velocity. So I'll just disconnect this velocity from this bind export for now, and then drop in an add bop, connect our current velocity to that, and then connect the difference between the wind and the current velocity. But ultimately, I don't want to change the y vertical velocity of this dust. I really only want to affect how it's traveling horizontally. So to make sure that we just maintain our existing y value for the velocity, I'm going to drop in a vector to float, connect our velocity to that, and this gives us access to the individual x, y, and z components of our velocity. Now, before we write out our final velocity to the bind export here, we can use a float to vector to construct a new vector value from a few different float values for x, y, and z. So connect that float to vector to our bind export, and to make sure that we're keeping the exact same y velocity as our simulation already has, I'll take the y value from this vector to float, that's splitting up the velocity into its components. So that's going to be the second output here. Connect that to the second input on our float to vector. And on this float to vector, you can see that when we have nothing connected to these, they're just defaulting to use this parameter value in the UI here. So right now, this is going to maintain the y velocity from our simulation, but it's going to set the x and z velocity to 0. But we certainly don't want that. We want to get the x and z velocity that's been modified by adding in some of our wind here. So let's drop in another vec to float after this add sop, reorganize that a bit, drop in our vector to float, and then connect the summed velocities, which has our current velocity with the wind added, connect that to our vector to float, and then we can just grab the x and z components of that and connect that to our final float to vector here. So we're getting our x and z from this added together vector, our y velocity from the original, and writing that out to our new simulation velocity. Now this is probably going to look a bit extreme because we're forcing the velocities of the simulation to match the wind immediately on x and z at every time step. So even though this is likely going to look a bit crazy, it's still worth seeing what this looks like at this point with that extra velocity influence added. So let's exit our PyroSolver here and then run a new simulation of this update. Now our new simulation is looking pretty weird. We can see that we are successfully adding in some wind velocity to this dust sim, but this looks pretty crazy. It's adding far too much wind velocity and looks, pretty bizarre. So there are a few things going on here. Ultimately, yes, we do need to just add a multiplier to add less of this wind velocity. And we do want to add this height-based fall-off that I mentioned earlier because I'd like to have more wind force blowing at the top area of the simulation and less near the ground here. But one of the other sneaky problems with doing things like modifying the velocity in this VOPNet is that we're not only changing the velocity where our density is, we're also changing the velocity of all of the empty voxels as well. So all of this empty space is picking up this extra velocity that's pushing the simulation as well. And perhaps that's physically correct because in real life, sure, you would have wind velocity in the air, not just where the actual density is, but generally I find that it looks a bit nicer to just add this velocity influence where we have density values. So diving back inside our PyroSolver and into our gas field VOP, we can do a check on the current density value to only add in some wind when the density is above 0. So we can drop in a compare and connect the density to that. And for the test, we'll select greater than. And for the float, I'm not going to compare to 0, although perhaps it's fine, but I like to instead put in some very small density value. So I'll put in 0.000001. So this comparison will output 0 if this is false and 1 if this is true. So this velocity that we're adding into our simulation velocity can be multiplied by the output of this check. So when it's multiplied by 0, it won't be adding any velocity, but when it's multiplied by 1, where the density is, it will add the full amount of wind velocity here. So let's just make a little bit of room for that. I'll pull my wind and subtraction and velocity to the side. Let's drop in a multiply and put this between the subtract and where we add that into the velocity, and then connect our compare output to that multiply as well. So let's jump out of our PyroSolver and flipbook our new sim. Now after adding the check, to only add this extra wind velocity where we have some density values present, things are looking a lot better. This is still far too extreme. It's not looking very nice because we really need to add that height-based multiplier on this and dial down the effect overall, but this is looking much better than before we added the check. So just pulling up that previous version for reference, and this one, we added the velocity everywhere, including the empty voxels. So yeah, this is not looking very nice. And if we put this side by side with our updated version and go to the same frame, and even just looking at a static frame here, you can see that the version on the left, where we added the density check, that's looking much nicer than the version on the right here, where we're also adding the wind to the empty voxels as well. And now to add the height-based fall-off to this effect, let's go back inside our PyroSolver and back inside the gas field VOP. And we're going to add an additional multiplier that we can wire into our existing multiply here. So this new multiplier is going to be based on the Y position of the voxel. And to get just the Y height, we'll drop in another vector to float, connect that to the voxel position P, and then we can use a fit function to remap a multiplier based on that Y height. So drop in a fit range, and we'll connect the Y height by grabbing the second output of our vector to float, connect that to the input value on this fit VOP, and now we can add some controls to specify the minimum and maximum height. So I'll drop in another parameter. This one's going to be a float. I'll name this wind height min, and same thing for the label, wind height min. Drop in another parameter, call this one wind height max. Once again, same thing for the label. And now connect the wind height minimum to the source minimum on the fit, the wind height max to the source max on this fit. So this is going to take the Y position between the min and max height and map that to a 0 to 1 multiplier here. So we can connect this fit range to our multiply that also includes the multiplier for that density check. So you can stack up as many multipliers as you want on here. And with those min and max height parameters added, we can jump out of our VOPNet here. You can see we have those parameters available at the top of our gas field VOP to easily control this here. So sure, you could enter in your own values, perhaps ramp your multiplier from a Y height of 0 up through 50. It's totally fine to do it this way, but I often like to do this sort of thing visually in the viewport. So if we exit out of our PyroSolver here, I've just created this reference box in my scene. This doesn't have to be a box, you could use any shape that you want. And this is a nice and convenient way to specify this because you can really visually see exactly where the minimum and maximum influence will start and end. So you can adjust your reference object to your liking and then add a null so that we can reference this a bit more easily. I'll call this wind height ref. And then diving back inside our Pyro solver, for the wind height min and max parameters here, I'm just going to reference the height of that object we just set up. So we can use the bbox function. So if you type bbox, you can see this takes a path to the node that you want to measure. And then for the second parameter, you can enter in one of these options here. You can grab the minimum, maximum values for X, Y, and Z, or you can grab the size values. For this, I want Y min and Y max. So I'll point this bbox lookup to object context /dust /wind height ref, and then type in d underscore Y min. And you can verify that's working properly by left clicking on the name of that parameter. This will show the value that it's measuring there. Then I'll just copy this expression, paste that into the height max, and instead of Y min, we'll type in Y max instead. Then left click both of those to see the range that this is picking up from our reference object. So this sets up a multiplier on our wind force from approximately Y height of 6 to 26. And then once again, we'll run a new simulation to check out this update. So now reviewing our updated sim, you can see that the fall off based on the Y height does look like it's working correctly. We're not getting nearly as much wind being applied at the bottom portion of the sim as we are up in the top portions. So this is all good from a technical standpoint. This doesn't look very nice artistically, but we just need to turn down the overall amplitude of this. So let's go back to our Pyro solver, dive inside here, back inside our custom wind VOPNet. And to tone down the overall effect, we can just change this destination max value here. So you can just change it in the fit range UI if you want. Or if you want to keep all of your parameters nicely on your custom wind gas field VOP, we can add another parameter. I'll call this wind strength, same thing on the label, and then connect this to the destination max. So instead of remapping this multiplier from 0 to 1, that multiplier will go from 0 to whatever we set on this wind strength parameter here. And because this effect is looking quite extreme right now, and I want the wind to be much more subtle than this, I'm going to set a fairly low wind strength here. Of course, you can play around with setting this to your liking, but for my final sim, I wound up going with a strength of only 0.04. So now, jumping out of our Pyro solver once again, we can set up a new flipbook for this, which should be our final simulation. And for this one, I want to bring in the rest of the terrain as well for reference. So, up near the top of our collision volumes, I'm just going to drop in a new object merge, point this to object /fracturing /out static region, and then drop in a merge under that. And currently we're template viewing our destruction sim with our creature here. So I'll connect that merge to this other merge here, and then add our out static region to that. Call this merge viz, and then template display this. And when we run these flipbooks, we're running the entire simulation and getting some images back of this, but we're not caching this out at the same time. So if we just run a flipbook of this, which we expect to be our final simulation, then it could be kind of a waste to run a flipbook, see if we like it, and then rerun that same simulation to write it to disk. And these dust sims can get fairly heavy, so right now it's not saving very much of the simulation in memory. If you look at our timeline here, it's only saving a few frames in memory, and you can increase that a bit by going to the Pyro solver, and then on the simulation tab, you can turn up the cache memory here. So this will allow it to save more frames in memory, but there are still limits to that, and you can only push that so far. So we can set this up to cache out to disk while we're flipbooking it. So if you drop in a file cache, connect our Pyro solver to that, and let's point this file cache to our destruction directory and make a new directory for this dust sim. And we'll call this dustsim.$f3.bgo.sc. So now if we display this file cache and rewind our sim, the default file mode here is no operation. And if we pull up that location on disk, you can see we don't have any files here being generated at all. But if you set this to automatic, then you can see this is writing those files out. Same thing if we set this to write files and advance one frame. You can see that's also working to write out these files to disk. So I'll rename that file cache and frame up our shot here, and then run a new flipbook of the entire range. And now reviewing this latest update to that custom wind force, everything's working quite nicely. You can see the top portion of the simulation here is picking up much more wind influence than the lower areas near the ground, and I'm pretty happy with how this is all looking. Of course, there are always things that we can tweak endlessly on this. For example, right now we're starting with 100% density sourcing and dialing it down to about 50% by around this point, and I do feel like we could probably lower the density further by this point in the sim. You could probably take the density sourcing to just about 0 by the end of the shot here. And yeah, you could tweak this stuff forever, but I'm pretty happy with how this is looking overall, so we can start setting this up for rendering. Before we start setting up the render for this though, make sure to turn on the load from disk if you use that workflow that I just did, where you save out the cache frames while you're flipbooking the sim with the file cache set to write mode. If you don't turn on load from disk, then you're risking accidentally overwriting simulation frames later when you're just scrubbing around the timeline, and that can mess up your cache. So turning on load from disk is very important. And now let's drop a null after our file cache here. I'll call this out dust sim. And we have to put this back into the actual rendering space because we're still at simulation scale here. So let's grab one of our sim scale transforms, copy that, and paste that in underneath our cache here. We'll connect that up, rename this to sim scale invert, and then on the transform settings, select invert transformation, display that. You can see it's now pushed back into rendering space. We can add a null after this to refer to this in our render object. We'll call this render dust sim. And you can see that after transforming this into render scale, it's showing up a lot denser than it was at the sim scale. And this is something that you can always expect to happen when you're transforming up volumes like this, and it's not really a problem because we're ultimately going to dial in the final look of this dust in the shader, and we can control the density there. So don't be too alarmed if it does look a lot more dense after scaling it. And if you'd like, you can change how this displays in the viewport as well. Previously, we had controlled this on the Pyro Solver under the Look tab, which is assigning a shader with some different properties to this. And we can do the same thing after caching this out as well. You can drop in a Pyro Post Process, connect that to the render null here, and this is essentially going to do the same thing as what the Pyro Solver's Look tab was doing. This gives us all the same controls to set a shader on this volume. So we could scale down the density a bit to match what it looked like in the sim scale. We can turn our smoke color back down, turn off the fire emission, can turn our shadow density back down a bit as well. So this allows you to really control the look in the viewport even after caching it out. And this is only controlling the look via a shader on the object, but you can also change the actual values themselves. So you can use various tools if you want to modify the density post-simulation. Now you could use a volume wrangle. So if you display that, we can say at density times equals 0.3. That's going to multiply down the actual density values and the actual volume. And you can do similar things, perhaps with a volume VOP. Connect that to the render dust as well, display the volume VOP, and dive inside there. So you could just set a basic multiplier here in VOPs by dropping in a multiply constant. I'll set this to 0.3 as well, just like we did with the wrangle. So you can see that's doing the same exact thing, and it's turning down all of the actual values in this density volume. Of course, you could get more fancy than this in a BOP network and do some nonlinear remapping of those density values and things like that. In this case, we don't really need to mess around with that. Just wanted to show you a few options that you do have to change the way this looks and change the actual data post-simulation. We do have some other more simplified tools as well. You could drop in a volume mix and change the multiplier on here also. So changing that to 0.3, we'll do the same thing that we just did in our BOP network and in the Wrangle. And because we've cached this out as a VDB, we also have various VDB operations available as well. So if you type in VDB, you can see lots of VDB specific tools that you can use to modify this volume. So we don't really need to use any of this stuff in this case. I'll just drop a netbox around that and call this options for post-processing. And I'll leave this in the example HIP just for your reference, just so you can see a few things that you can use to modify that data post-sim. And now that we have everything all cached out and rescaled into the proper rendering space, we can go ahead and actually start setting up the render for this.